Welcome to our deep dive into what's basically the rule book for reality itself, Euclid's geometry. Let's jump right in.
So let's kick things off with a huge question, one that thinkers have wrestled with for literally thousands of years. It's the whole reason geometry even exists. How can you prove something is absolutely 100% undeniably true? Like, how do you build knowledge on a foundation that you know for sure won't crumble?
And this wasn't just some abstract philosophical debate. It was a real down-to-earth problem for people like the ancient Egyptians. Imagine this. Every single year, the Nile River floods and just wipes the slate clean. All the boundaries for your farmland? Gone. Without those lines, how do you know what's yours and what's your neighbor's? It's total chaos, right? So to fix this mess, they needed a system, a set of rules that everyone could agree on to bring order back from all that chaos. And that is where geometry comes in. The word itself is super cool. It comes from the Greek geo, meaning earth, and mitrain, meaning to measure. So they were literally measuring the earth to redraw those all-important lines.
Okay, so here's what we've got on the agenda. We're going to cover why geometry exists in the first place. Then we'll get into Euclid's amazing system of truth. We'll check out the rules for all math, the axioms, and the special rules just for geometry, the postulates. And then we'll put it all into practice and solve a problem Euclid style. And trust me, getting this logic down is huge, not just for your exams, but for understanding how everything from computer code to legal arguments are built.
All right, time to meet the man himself, the master organizer of math, a Greek guy named Euclid. So way back around 300 BC, he looked at all the math knowledge that was just kind of floating around, all scattered, and he did something incredible. He built a complete logical system from the ground up. His big idea, which he laid out in his masterpiece Elements, was to start with things that are so ridiculously obvious they don't need any proof. He called them obvious universal truths. Then, and this is the brilliant part, he used these simple truths like Lego bricks to build and prove way more complex ideas. This whole method, it's the absolute foundation of logical thinking. Okay, so Euclid split these obvious truths into two buckets, and paying attention here is super important, especially for any exams you've got coming up. First, you've got axioms. Think of these as the universal laws of all math. They work in algebra, arithmetic, the whole shebang. Then you've got postulates. These are the special rules that apply only to geometry, all the stuff about lines, circles, and shapes. So let's start with the axioms. These are the big guns, the powerful, common-sense rules that are basically the backbone of all mathematics. And here's the thing, you probably use these every single day without even thinking about it. All right, here's axiom number 1, probably the most famous of them all. Things which are equal to the same thing are equal to one another. Yeah, it sounds a bit formal, I know, but it's basically the logic behind substitution, something you use constantly in algebra. Let's look at a really simple example to see what it means. So, check this out. If John's age is the same as Mohan's age, and Ram's age is also the same as Mohan's age, well, it's a no-brainer, right? John's age has to equal Ram's age. It's simple, it's logical, and it's always true. That's an axiom for you. Okay, next up, axiom 2. If equals are added to equals, the wholes are equal. Now this is the absolute bedrock of solving equations. Seriously, every time you add, say, 5 to both sides of an equation to solve for x, you're using this ancient Greek rule. I mean, just look at this example. If Ram and Ravi have the exact same weight, and then they both gain 2 kilograms, well, their new weights are still going to be equal, right? It's like a balanced scale. If you add the same thing to both sides, it stays balanced. This is the key idea that lets us mess around with equations and still know the result is valid. All right, let's jump to axiom 5. The whole is greater than the part. Now, this one sounds, well, duh, right? It's so obvious. But that's the whole point of a system like Euclid's. You can't assume anything. Even the most basic fundamental truths have to be written down as official rules. And what's a better way to explain this than with pizza? I mean, come on. A whole pizza is always going to be bigger than a single slice you take out of it. It's completely obvious, for sure, but now it's an official mathematical rule we can use. Okay, so we've got the rules for all of math down. Let's switch gears and talk about the postulates. These are the special rules that build the world of geometry itself, the world of shapes and figures. These are the rules that let us actually draw things and reason about them. So the first few postulates are really straightforward, pretty intuitive stuff. Postulate 1, you can draw a straight line between any 2 points. Yep, makes sense. Postulate 2, you can take a line segment and just keep extending it forever. Got it.
Postulate 4. All right angles are identical. All 90-degree angles are the same. Check. Simple enough, right? But then there's the fifth one. And oh man, this one is special. It gave mathematicians headaches for literally centuries. And here it is, the famous, or maybe infamous, fifth postulate. Yeah, I know, just looking at that text makes your eyes glaze over. It sounds so complicated. But don't panic. A simple picture makes this whole thing crystal clear. See? Way simpler with the picture. All it's really saying is this. You've got a line crossing two other lines, right? Look at the two angles on the inside, on the same side, angles 1 and 2 here. If you add them up and they're less than 180 degrees, well, that means the two main lines, A, B, and C, D, are leaning in toward each other. And if you keep drawing them out on that side, they are guaranteed to meet eventually. That's it. Look, that fifth postulate is a total mouthful. So here's a pro tip for your exams, a real lifesaver. Mathematicians came up with a much simpler equivalent version called Playfair's axiom. It just says this: for any line and a point that's not on it, you can only draw one single line through that point that is parallel to the first line. Just one. It means the exact same thing as Euclid's clunky version, but it's way, way easier to remember and use in a proof. So if you remember one thing, remember this one. Okay, we've got our rulebook, we have our axioms and our postulates. Now for the fun part. Let's actually use them to build a logical proof, exactly like you'll have to do on a test. This is where we put all the pieces together, the definitions, the axioms, all of it, to prove something new is true. So here's a classic problem you might run into. We're given a couple of facts. First, the line segment AC is the same length as the segment XD. Got it. We're also told that point C is the exact middle of line AB, and point D is the exact middle of line XY. Our mission, should we choose to accept it, is to use our new rules to prove that the total lines AB and XY have to be equal to.
And we're going to solve this step by step, like a detective laying out the evidence. Step 1. Always start with what you're given. We know AC equals XD. We write that down. Step 2. Use your definitions. We know C is a midpoint, so the whole line AB has to be double the part AC. Same goes for XY and XD. Step 3. Connect the ideas. Since the little parts, AC and XD, are equal, well, their doubles have to be equal too, right? So 2AC must equal 2XD. Step 4. We bring in an axiom to seal the deal. Axiom 6 says things that are double of the same things are equal. So we can officially, logically conclude that AB equals XY. Boom, that's how you write a perfect proof.
So you might be thinking, why does any of this ancient Greek stuff matter today? Here's why. You're not just learning about triangles and lines. You are learning the fundamental operating system for logical thinking. This exact step-by-step process is used everywhere. A lawyer building a case, a doctor diagnosing a patient, a programmer writing code that doesn't crash. It's all based on this.
And really, this structured way of thinking is a genuine superpower. So the big takeaway here isn't just about geometry. It's that when you master this method of starting with simple, undeniable truths and building your way up to a complex, proven conclusion, you're basically learning how to think, how to prove things, and how to create, well, anything in any field you can imagine. And to think, it all started with a few simple rules about land and lines.